Convolutional neural networks have become a really hot topic for computer vision applications in the past year. And so we've put together a complete track today focusing on the implementation, practical implementation aspects, since that's the focus of our event. And that's going to be the focus of the next presentation, which is by Bruno Lavigueur from Synopsys. Bruno's a project leader in embedded vision at Synopsys, and what he's going to talk about is how convolutional neural networks of the very same kind that Ren was talking about can be simplified and streamlined to be implemented in constrained environments, power-constrained, cost-constrained environments where you don't have a supercomputer. So I think you're going to find this material very interesting. Synopsys has been very active in developing architectures and development techniques for implementing convolutional neural networks in power and cost-constrained systems, and Bruno's been one of the key guys doing that. So with no further ado, I'd like to introduce Bruno Lavigueur. If you could bring up his slides, please.
Okay. So thanks a lot for having me here. It's a pleasure. And today I'm going to talk, like Jeff said, about convolution neural networks, but tailored for low-cost, low-power implementation. So something a bit complementary to what we've just seen in the keynote where CNN were used to crunch on big data. So a single introduction slide about who Synopsys is for those that don't know. So at the base, we're an EDA company that provide tools to design your chip and implement them on silicon. We also provide tools to verify those designs, and more recently, tools to also verify your software. And at the center here of this slide, there is IP. We are an IP provider with a broad portfolio of silicon-ready IP. And the embedded vision platform we're developing is actually built by reusing many of existing IPs that we have that are also sold separately. And this is what I'll be showing today. All right. So I won't go into too much detail as to why neural networks are interesting, because we've seen the keynote this morning that talks about that. But just to say that today, the majority of the published CNN applications are not tailored for embedded devices. They have huge memory requirements, and they require a lot of floating point operation. So the question we can ask ourselves is, can they still be used on a low-power embedded device? Because they have a good detection rate and are quite flexible. And also, it's a pretty regular compute pattern that is implemented in neural networks. So they lend themselves pretty well to optimization. So the two main questions I'm going to look a little bit at during this talk are, can we reduce the size and the complexity of the neural net without impacting too much the detection rate? And also, do we need to use floating point absolutely, or can we have some fixed point implementation that still perform well in terms of detection rate and quality of results? Okay, so we're focusing on how the CNN works once it's trained. So we've seen that earlier today. It's a refinement process, multiple layers. That's why it's called deep learning. And the last layer will do the final classification. And this is just to show visually a bit what's happening throughout the layer. So as you move forward, you get, in this case, it's a phase detection, as you can guess. You get more and more abstract representation if you dump the internal values of the network, a more and more abstract representation of the initial phase. And that's what is used in the end to decide if this is indeed a phase or not. And at each layer, also, the other, I guess, key part of the CNN is that you subsample or you do max pooling or both to sort of zoom out and be able to detect bigger features, or a face in this case, but with smaller convolutions that don't cost too much to implement at runtime. And as I had said before, it's a pretty regular computation, and actually each layer, they all do pretty much the same thing, which is shown here. So you have a bunch of inputs, and you do a convolution, fixed size convolution kernel on those inputs. You combine those together, few or many or all of them, if it's a fully connected layer. You add them together. And then you apply a nonlinear activation function that's going to tell you if your neuron has fired or not, if you will. And these activation functions, they can be things like hyperbolic tangent, or more recently, a simple rectifier that gives a max between 0 and your accumulated value. So this is the compute pattern that is repeated over and over again, millions of times throughout your application. So given this compute pattern, it's quite easy to see that there's many straightforward ways that you can optimize such an algorithm. So you can use a vectorial or SIMD unit if you have them on your processor. You can use a GPU quite efficiently also. Or you could implement a more specialized type of machine like a systolic array type implementation that does streaming, because that's pretty much what a convolution neural net graph is. And no matter what you choose, to implement this, you'll have a performance power area trade-off, and you'll be limited in the size of the network that you can do by the usual suspects, the amount of memory you have, the bandwidth to that memory, the maximum number of operations per second that you can sustain. And that's what's going to impact, the size of the graph that you can implement. So to show this with more schematically, what are the parameters that impact the size of a neural network? And here I'm not talking when we're training it, but really when it's a trained graph is running. So the main parameters are the number of layers, so the depth of your graph, the size of the convolution kernels. So typically it goes from 5 by 5 all the way up to 11 by 11. And if you have smaller kernels, obviously you'll do a smaller convolution, and that will simplify the calculation. And the number of connections between the layers. Each connection requires its own set of coefficients for the convolution. So that will also determine, the memory size that you need to store all those coefficients. And the final consideration that's going to impact the complexity of the hardware you use to run those graphs is the data precision that you use. So floating point, or a 16-bit fixed point, or 8-bit fixed point, and this will impact the cost of your arithmetic units. So just to give an idea of what I mean by big or small graph, we've seen some pretty big ones this morning that have impressive performance. But here we've done some work, and this is a graph that has been done by a company we've partnered with called Multicoreware. And they've generated a graph that was trained on about 10 million faces extracted from movies. And they trained a pretty big graph that looks a little bit like the now classic AlexNet type graph that came out from University of Toronto a couple of years ago. And it's a decent-sized graph, as you can see here, that has pretty good detection rates. Since it's been trained, with movies, it's maybe a bit geared towards finding out good-looking people, but still, overall, no matter what you throw at it, you have good accuracy, good F1 scores, which is the sort of the mean between precision and recall, and a fairly hefty amount of weights for a convolution, 400 megabytes, 7 convolution layers, 3 fully connected layers at the end. And they've created also what I call here an embedded version of that graph, which is orders of magnitude smaller, as you can see. Only 500 kilobytes for the weights, a lot less layers, and about 200 times less compute requirement. Yet, the detection rates and the accuracy have only went down by a percent or so. So it's still quite usable in many different application scenarios, while this time being much more realistic to implement on a system that's going to be, battery operated, small areas, low power. So how did they move from this big graph to the smaller one? This has been done using existing popular training frameworks like CUDA ConvNet, Caffe, TNO, or Torch7. And it has been done initially without worrying about the precision. So training done in all the training done in floating point, the gradient descent, and all that. And two approaches have been tried out. The first one is a from scratch approach, where since the network you're trying to create is small and you're limiting the number of layers and so on and so forth, you can actually, without building your own supercomputer like we've seen this morning, you can actually use a bit of a brute force approach where you take many shots on goal and you try to many different scenarios and keep the ones that pan out to work better. And also the other approach that was used is, since there already was an existing graph performing well, but a big one, it was iteratively reduced by retaining at each time the best candidate. And in the end, both approaches yielded similar graph with similar detection rates. Once you have a CNN graph topology, if you want, that is satisfying and is training well, you still need to do some optimizations on your training to get good results. And those are the classic ones. So data normalization, the hard negative mining or boosting, where you take part of the true, the false positives that you get, and you send them back as input that have been now labeled as not what you're looking for. Data augmentation, which is important, to avoid overfitting and also to generate more training data, because as we've seen this morning, you never have enough. And with this small graph that I've shown 2 slides ago, the initial simple training had a so-so detection rate, but by applying those techniques, it was brought to much more satisfying results with a F1 score of about 90%. So at that stage, we had a graph that was still using floating point, but was a good size to target a low power embedded device, and was still having detection rates, that were good enough to have interesting applications based on that. And to keep our hardware simple, we wanted to try to implement this without using floating point arithmetic. So how this was achieved is, your input is already pixels, either typically 8-bit, sometimes 16. All the coefficients for a convolution, we know them because we're done with the training. And typically, if the training is good, you'll see that all your weights are close to 0, positive or negative. So a few bits for the integer part is enough, 1 bit for the sign, and the rest we keep for the decimal, the fractional part. In this example here, I say we use 16-bit for those weights. And the many experiments we've done, sometimes you can go down to 8 and it doesn't impact your detection rate. 16 seems to always be enough. Then obviously your accumulator needs to be wide enough. That's nothing new. And maybe the part that is slightly more challenging is, Since now all the neural network graph that train well are using the rectifier instead of a sigmoid or a hyperbolic tangent, you don't have at each layer a sort of a firm guarantee of what your max value will be, because the rectifier is just a max between 0 and x. So you need to look at what you, but however, since your weights are well balanced around 0, when you do the convolution, you don't get huge values. So by applying some well-chosen value for n here to shift the output of your nonlinear function, and also apply a little bit of saturation when you have only a few numbers that are too high, we can keep the precision to like a 16-bit fixed point implementation, and we basically see only a fraction of a % change in the detection rate by doing those changes. Okay. So here, to test this, we've also used another database that is not the one extracted from the movies, which is, in this example, we used the FDDB database, which is just a bunch of pictures, often with bad quality, out of focus faces, that type of stuff. So to have a test set a bit challenging. And we tried different version of our fixed point small CNN graph on it. And what we've seen is that although we are not performing as well as the best published result here, our numbers are pretty much competitive with the average of the different published results. And in this case, we were using only 8-bit fixed point implementation. With a test like FDDB, you're scored also based on localization. So what we see here with the red ellipses is the ground truth that they've labeled manually. And it's considered a good detection if you overlap 50% with it. And like one of the examples you see here, we drew the ellipse with a light blue. And that's a detection that our localization does not overlap by 50%, so it's not considered as a hit. But just to say that here we didn't optimize too much, like the non-max suppression that is done at the end to do localization with all the boxes that you get. Because CNNs, when they're trained, you send some training data that has been shifted, scaled, so you have some invariance to towards look at where the face is in your detection window. So you'll typically get many hits for a single face in this case, and then you need to do some non-max suppression to recenter your box around the face. But still, even though it's not the best results published for application like video surveillance or things like that, it still performs very well, and it can be a small, low-powered graph, which is quite interesting. So, on what type of hardware has this been implemented? It's shown here. We have there's two main parts in this vision subsystem. On the left-hand side, you have a set of general-purpose RISC processors that can be used to run pre- or post-processing around, before or after you do the CNN, because you always need to do some pre- and post-processing for a full application around CNN, typically to do some color space conversion or scaling, or create a pyramid of your image to begin with, and then to analyze the results that you get out of the neural network at the end. So that type of operation can be done on the RISC course here. And the CNN engine itself is based on a configurable number of processing elements. All of them are symmetrical. They have a load store interface to fetch image input and the convolution weights from memory and bring them to their local memory. And they have a reconfigurable streaming interconnect used to implement communication between the layers of the graph, if you will. So let's say the P number one process data in layer one, then he can push it in some point-to-point FIFOs to the next processing element that will carry on. These processing elements have been, they're programmable units with a C compiler and all that, but they also have a set of optimized instructions that are geared toward implementing efficiently CNN graphs. So optimizations for convolutions, obviously, multiply accumulate, some lookup table, and also some micro DMA that can run in parallel with the convolution to get the next data while you're processing the current one. So just an example of how a graph can be mapped on this hardware. So yeah, here to keep the diagram simple, I'm using a configuration with 4 processing elements. That are the 4 green boxes at the bottom of the slide, 5 FIFOs. And the graph that is shown here, the layer number 3, has many inputs and many connections, and it requires more computation. So it's been split on 2 cores that I've called layer 3A and layer 3B. And the image is, in layer 1 and 4, since they're small in this example, they've been merged together on 1 core that alternates between the 2 of them to keep it busy. The first core here on the left, it fetches the image input only once, line by line. And then the intermediate results of the hidden layer are streamed between the cores. And at the end, they're sent back. The detection windows are sent back out to be analyzed. Some performance figures that we get with this. So we can see in the case, for example, of a 5x5 convolution, we take on average 30 cycles to do 8 of those in parallel. It's a 8-way MAC unit per core. This includes all the contention and data movement. And when the graph is well balanced, we can keep our MAC resources utilized around 85% of the time. And here you have also, if you target with this, it's a soft IP. So if you target with this, for example, 28 nanometer HPM process, you'll get around 15 milliwatts per processing element with their memory. And we have also this running as a demo that you can come and see this afternoon of this such an embedded CNN graph that has been reduced in its size and also turned into a fixed point implementation. And that we run on an FPGA prototyping platform called HAP70, just to show it running at obviously a fraction of the speed you would get in a real ASIC. Okay, so what lessons can we take out from this experiment? Well, the first one is that you can dramatically reduce the complexity of a CNN graph if you're willing to sacrifice a little bit, but only by a fraction of a percent, for example, your detection rates and the quality of your results. And but however, to have those good results, the offline training that you will do is still a critical step. And this training, you will need to do it with a good compute farm still to try many different scenarios and test them out. we've seen that having specialized and programmable hardware that can be used to efficiently implement such graph and have them running, with low power and low area. But the other thing I can say though is that if you want to have an embedded CNN graph that is small, you probably won't be able to detect thousands or tens of thousands of different classes all at once. Like for example, in the ImageNet competition, you probably need a little bit more than 3 layers to do that. But if you're limiting yourself to a dozen or so different classes that you want to detect, what we've seen is that you can have some very, very small graphs that still perform, better than other classical techniques like Hog or Viola-Jones or hard gradients. And that can be optimized quite efficiently on hardware. And the last conclusion I would like to bring here is that as nice as convolutional neural net are, you always need to couple them with other processing steps to have a full application. Shrinking the image, creating a pyramid to be more scale invariant. Then also, if you're processing a video, you'll often want to look at results between frames to analyze, let's say, if I've done a detection of the same thing in 2 or 3 consecutive frames, maybe you have to do something different depending on your scenario. So there's still a need to have other types of algorithm around it also. And yeah, some links to other interested papers that if you want, you can look at that are also targeting some embedded CNNs. And also the link to the Synopsys offering that will be demonstrating this afternoon at tables 3 and 4 at Mission Ballroom. So that's where I'll stop for now. And if there's any questions, I'll be happy to take them.
Yeah, I think we have time. I think we have time for 1 or 2 questions. Do we have a microphone? There's a couple people with their hands up here. I can tell you right now we're not going to have time for all the questions, but let's do maybe a couple, and then if you wouldn't mind following up later, you'd be available during the lunch break.
I'll be here all day.
Okay, thanks, Bruno. Go ahead, sir.
Hi, Ganesh Desika with ARM Research. What was the programming model that was exposed to, I guess it was Multicoreware that designed the CNN? How did they actually go about programming your accelerator?
So the training is done with existing training frameworks like CUDA-ConvNet or Café. And once your graph is trained and you have a fixed point version of it, porting it to our hardware is done by manually writing C code for that. So today it's still a manual step that we're looking into automating.
Question here.
Yes, hi, I'm Joe Raffa. I have a question about your methodology for reducing a large graph into a smaller embedded graph.
Yes.
You described a methodology for doing it in a static way, calculating it and then deriving the best embedded graph and then putting it into the embedded device. Is it possible to do this in a more dynamic way? Maybe through some sort of a caching or paging scheme whereby, if the detection rates start to go down, that it could go back out and refresh with a different graph? Or version of a graph?
The way the graph has been trained is, so it's been trained on a GPU farm with scripting to try multiple different topologies, train them, test them, and then keep the best one. But the process of figuring out why a topology is working better than another, there's still some. You need to know a bit why and try to understand what's happening. So it's not completely automatic. You just send the data and you have a good graph at the end. You still need to think about and analyze the results you're getting. But all the tedious part of creating a configuration, launching the training on it, that can be automated.
Thanks very much, Bruno. I'm afraid we don't have time for more questions now, but please feel free to see Bruno later in the day at the Synopsys tables in the technology showcase in the room behind us. And please join me in thanking Bruno for a very interesting presentation.